We're going to spend the first half of this talking about composing functions in a very simplistic way. So in business, the term profit describes the difference between the money the businesses earn, revenue, which I'm going to define using the function R of X, and the money the business spends, cost, which we're going to define with the function C of X. So we'll start with the revenue function R of X. R of X, Grooming USA charges $25 for every pet that is groomed. Let X represent the number of pets groomed in a month. So if it's $25 for every pet groomed, then if we groom one pet, we make 25, two pets, we make 50, so on and so forth. And sometimes building a little table can help you kind of get the ideas down in your head about what's going on. Then it says on the next one, materials and labor for each pet groomed cost 15 for each pet groomed. That key right there means we're spending 15x on materials and labor, but we're also spending a fixed cost of $1,000. So C of X is going to be the cost function. This is a cost per month. Now, both of these equations represent a month, but that's okay. We could multiply them by the number of months if we wanted to with another composing of functions, but we'll keep this simple. What's important is to kind of really grasp is that profit, P of X, is equal to the revenue, R of X, the amount you take in, minus C of X, the cost. So if we start to make this a little bit simple, we could say that's equal to 25x minus 15x plus 1,000. We could even simplify that using the distributive property of multiplication across addition subtraction to 10x minus 1,000. So it says if we groom 93 pets, 95 pets, P of 95, plug that in, 10 times 95 minus 1,000, did we earn a profit? Well, 950 minus 100 is negative 50. No, we did not. We actually lost $50. And what would the profit be if the business groomed 110 pets per month? Well, we could just do P of 110 to be 10 times 110 minus 1,000. Oops. And minus 1,000 would then give me 1,100 minus 1,000 would be a profit of $100. Not very much. So we could explain all this further if we wanted to, but I wanted you to kind of have an idea. It says finally a business breaks even when its revenue equals its cost. So when R of X equals C of X. And how many pets would they have to have in order to break even? We could calculate that as well. We could say our R of X function of 25x equals our C of X function, 15x plus 1,000, and what x would make that true? Well, 10x equals 1,000, or x is equal to 100, and at 100 pets, we break even. So this is the essence behind working with multiple functions and figuring out how to do them. There are a couple of basic operations. One, we're going to add and subtract. This is the most simple operation that we can do. But if we add and subtract functions, for instance, if we have f of x is equal to something like 5x minus 1 and g of x is equal to something like x squared minus 2x plus 4, then the notation we can use could be something like this. We can say f plus g of x, which is the same thing as f of x plus g of x. I'll let you go ahead and calculate this, and I would like you to pause the video, calculate this, and come back to me with what that is. Okay, sorry, I had to throw a cat off the counter. Coming back, this would be equal to x squared. Well, let's actually write this out. It's 5x minus 1 plus x squared minus 2x plus 4, or x squared plus 3x plus 3. Now, we also need to concern ourselves with domain. This is going to be a little bit of the Algebra 2 part of this, or Algebra 2 honors part of this. So if I look at that original function, that's linear, and the domain of all linear functions is negative infinity to infinity. And if I look at this function here, its domain is also negative infinity to infinity. That is a quadratic, or an x squared. So if I add the two of them, I would expect that my resulting function also has a domain of negative infinity to infinity, since that is also a quadratic. So be aware that you could be asked about the domain of a composition of functions as well. We'll call this example number 1. Let's move with another one. Let's go with subtraction. And you may say, well, subtraction doesn't seem like it'd be that terribly complicated, and it's not. If I now say what is f minus g of x, and I use the same operators, I would get f of x is equal to 5x minus 1, and g of x is equal to x squared minus 2x plus 4. And I want you to make a note off to the side of what property you need to be careful of when you do this. Pause the video and come back. So you need to be careful of the distributive property. Write it out first. I would encourage you very strongly to write the whole thing out, and then to end up with negative x squared plus 7x minus 5. And if I look at the domain of this, it is also negative infinity to infinity. So watch the distributive property when doing this. That is adding and subtracting. Then we move into multiplying and dividing. Once again, we need to be careful of the different operations that can play out. So we'll set up another thing like the start. This is going to be a little thing. Let's say that the demand function, we'll call that demand d of x, is equal to 5,000 minus 10x. So this is going to be the demand for a company's new brand of cell phones. And so we'll say let x equal the price in dollars of the cell phone. So demand is this function. As the price goes up, the demand goes down. If the price is $0 by this model, the demand would be 5,000. So that's demand, and we have a price. What we know is that we can find a revenue function, R of x, which is equal to demand times cost. Demand just being the number of people who want to buy it. So that can be a little note we'll say here, demand. Sorry, I did not take home a very good pencil tip. Demand equals number of people who buy. So if I have revenue equals demand times cost, and I say that the demand function is this, and the number of people with the price function is that, then my revenue, R of x, is just equal to x. Well, let's put it in the right order. 5,000 minus 10x times another x. And that gives me this. We could even simplify that down to 5,000x minus 10x squared if I wanted to write the demand function. Now, we need to be concerned with domain. So the demand function, if I look at how this plays out with demand, I would want to take this demand function and maybe factor the 10 out to get a 500 minus x. So x can't necessarily be anything in the context of this problem. We know that the minimum cost would be 0 and the maximum cost would be 500, because any more than that, we start losing demand. So I would say that x is between 0 and 500, and it could technically include both of those, so 0 and 500. And that would be the demand part. The price, if I look at the domain of the price, so I'll kind of stick that up here. My demand price, my domain would be that x has to be, price just can't be negative, so x could be anything from 0 to infinity. And you can argue about whether you want to include 0, but it could be anything, 0 to infinity. The revenue function really needs to be the intersection. So the domain of this is the intersection of the domains of price and demand. So if that's true, then the intersection of 0 to 500 and 0 to infinity would just be 0 to 500. The overlap is just 0 to 500, and that would make sense to us, that the price really has to max out at 500. Okay, last example. So that was example 3, so let's go with 4. And your book's examples, we're limiting this up to their example 3, but I'll just call this number 4. We're going to go with dividing. So we said this is multiplying, dividing. Here's my dividing. Let's say that f of x is equal to x minus 7, and g of x is equal to 2x squared minus 13x minus 7. So in this case, we're going to try to define f divided by g of x, which is the same as f of x divided by g of x. So first we start off with what this looks like. X minus 7 over a 2x squared minus 13x minus 7. And you should always ask yourself the question, can this be simplified? This one can. If I factor the denominator, I factor into a 2x and an x. The 7 could not necessarily, oh no, the 7 would want to be multiplied by the 2, so that it is 7 and 1, 7 times 2 is 14, and then we would get a negative 14 and a positive 1, and then this would simplify and give me a 1 over a 2x plus 1. And note that we know that if I look at the final here, my domain would have to be x cannot be 7, and x cannot be negative 1/2. The negative 1/2 is clearly stated, and that's part of the domain anyway, but the x not equal to 7, we lost that information. So we'd want to include that, even though the domains of this beginning, both of these functions originally are both all real numbers, we can tell by dividing that the domain changes and becomes something different than it was before. So that's the essence of this. I don't want it to take too long on this video. We'll be back later, and I'll be back with part 2 when I come back.